All right, good morning, everybody. So at the end of last week, we were talking about implementing a stack using linked nodes. Right, now, remember the motivation for this is that we have two other stack implementations whose worst case push operation is big O of n. Right? Now, it's big O of n because in those implementations, you have to reallocate an array at some point when you run out of capacity in the underlying array that stores the elements. Right? Every time you reallocate the array, you have to copy the elements in the array, so the operation is big O of n. Right? Now, also remember that most of the time, though, push for an array-based stack is big O1. So there's not really there's not a strong motivation to not use an array-based list or an array-based stack or an array list-based stack. Right? But if you do need to guarantee that push happens in big O one time, you can change your implementation to the one we're going to do today. So we're going to use this node thing, or this node structure. Well, remember what a node is. So a node stores an element, right? And it also stores a reference to the next node in the sequence, right? Which we're going to call a link. Now, for the if the stack only has one element, that link is null because there is no other next node in the sequence. Right? When you push an element onto the stack, you make a new node. Right? So keep that in mind because in our push implementation, obviously we're going to have to make a new node in our in the method. So if I push a B onto the stack, I make a new node to hold the B, right? And then I set its next link to point to the current top of the stack. And then you adjust the top of the stack so that it now points at the new node. Right? And then you increase the size of the stack by 1 because we just added an element to the stack. Right? To pop an element off the stack, right, you remember what's currently sitting at the top of the stack, so that's the C. Right? You move the top of the stack to the next element in the stack. Right? And the way you do that is so top points at the top element. Right? The top node has a next link that points to the next node in the sequence. So what you do is you just follow that next link to go to the next node. Right? And then you decrease the size of the stack by 1 because you've just removed an element. Right? And then, of course, you return the element that was popped off the stack. Right? So what does our node class look like? Well, every node, right, needs to store an element. Right? So each node is an aggregation of one string, right? Because we have a stack of strings for the time being. Right? Furthermore, every node has a reference to the next node. Right? So every node is an association or is associated with another node. Right? Possibly null. Right? And so that's what your UML diagram looks like. Right? What is our node? Oh, so our node class. So here's our linked stack class, right? So a linked stack has a size, right? The number of elements in the stack, right? And it has a reference to the current top of the it has a reference to the current top node of the stack. Right? What does the node look like? Well, the node class is defined inside of our linked stack class, right? And it's defined as a private inner class, right? So a private, nested class, right? So it's private, which means only the linked stack class can use the node class. Right? So the node class is not visible outside of linked stack. Right? It's going to be a static class, a static nested class. Static nested class, that's correct. Static nested class, so I'll explain exactly what static means in a second in this context. Then each node, right, is made up of an element, right, and has a link to the next node. Right? The constructor doesn't do anything except set elem and next. Right? So we have a constructor that takes in an element and a next node, and it simply sets this elem to elem and this next to next. Right? So it doesn't have to make a new element. It doesn't have to make a new node, right? Because we're using aggregation and association here. Right? If we were using composition, we'd have to make a new something. Right? But there's no point in using composition in this context. Okay, so what's a static member class? Because that's what this node class is. Right? So a static member class is the simplest kind of nested class in Java. So in other words, it's really just a class defined inside of another class. And that's all it is. Right? Now, unlike other kinds of nested classes, so remember in the iterator implementation, we had a inner class, right, which is different from a static nested class. Right? So unlike other kinds of nested classes, a static member class cannot refer to the private members of the enclosing class. So all that means is node does not see size or top belonging to linked stack. Right? So node can't access the fields of the linked stack. Right? If it needs to access the fields, then it needs two things. It needs a reference to a linked stack, and then it needs a method in linked stack that gives them access to these things. Now that's the other difference, right? So in a static member class, where does it go? Oh, hey, wait, that's not. Oh, it's not on the slide. Okay, so in a static nested class, the nested class does not have a reference to the enclosing class. Right? So in other words, if you make a node object, right, that node object does not know about the linked stack object that made it. Right? That's different from an inner class. Right? So in an inner class, if you make an instance of the inner class, it has a reference back to the outer class object. Right? But in a static nested class, that's not the case. Right? So nodes know nothing about linked stacks. Right? They're completely independent. And that means you can also have a node object without having a linked stack object. Right? So they can exist on their own without needing an instance of the enclosing class. All right, so what does our constructor for linked stack look like? So our default constructor simply makes an empty linked stack. Right? So an empty stack has a size of 0, right? And it has no top node. Right? So we set that to null. How do you return the size of a linked stack? Well, I've got this field called size that holds the size of the stack, so I just return this dot size. Right? Now what about pushing an element onto the stack? So remember what you do, right? I want to push a new element onto the stack, so I make a new node to hold the element. Right? I set the new node's next link to point to the current top of the stack. Right? Then I adjust the top of the stack to point to the new node. Right? And then I add 1 to the size of the stack. Right? So it's just 4 steps. Right? And I can do step 1 and 2 in one line. Right? So I want to make a new node to hold the element, and I want to set the link of the new node to point to the current top node. Right? So I can just make a new node. Right? It's going to store the element, and its next link is going to point to the current top of the stack. Right? That's it. Right? Adjust the top of the stack so that it points to the new node, so this top equals n. Right? Increase the size of the stack by 1, so this size plus plus, and that's it. Right? So it takes 3 lines of code to implement push. Right? So it's almost as easy as the push implementation for an array list-based stack. Right? So an array list-based stack, you just add the element to the end of the list. Right? Here, you just make a new node and adjust a couple of fields, and you're done. Right? Notice that it's a lot easier than the array-based stack. Right? So remember, in the array-based stack, you have to check, is there room in the array to store the element? Right? If there isn't, I have to reallocate more space. Right? And then I have to make the array point to the new array, and then I can finally push the element onto the stack. Right? Here, it's just make a node, adjust top, adjust size, and you're done. Right? Now, if you look at this code, right, none of that code, right, depends on the size of the runtime of this code. Does not depend on the size of the stack. Right? So you make a new node, right? That just takes how much time it takes to make a new object. Right? You adjust top, and then you adjust size. Right? So push for our linked node-based implementation is big O1. Right? Takes a constant number of operations to implement push. Right? Does not depend on the size of the stack. Right? So that guarantees big O1 complexity for your stack implementation. Right? Now what about pop? So pop's also easy. Right? You remember what's currently sitting on the top of the stack. Right? So I remember that the C is currently sitting on the top of the stack. Right? I adjust top to point to the next element in the stack. Right? I subtract 1 from the stack size, and then I return the reference obtained in step 1. Right? So again, it's just 4 steps. Right? So here I'm going to, so ignore the if statement for now. Right? So step 1, remember what's currently sitting on the top of the stack. Right? So how do I get to that element sitting on the top of the stack? Well, I get the node, right? So that's this dot top, right? And then I get the node's element, right? So this dot top dot elem. Now notice that the linked stack class is able to access the private fields of the node class, right? So in other words, the linked stack can go into the node class and look at elem and next directly. Right? The opposite's not true, right? If you have a node object, the node object cannot look at the size or the top node of the linked stack. Right? So the outer class can see inside the inner class. Sorry, the outer class can see inside the static nested class. The static nested class cannot see outside to the enclosing class. Step 2, adjust the top of the stack so that it points to the next element in the stack. Right? So the trick here is to get to the next element of the stack, right? You start at the top, right, the top node, and you just follow its next link, right? Because next points at or refers to the next node in the stack. Right? So this top is just equal to this top dot next. Decrease the size by 1, and then return the element that you popped off the top of the stack. Right? So just the 4 steps. Now there's one more step you have to do. Right? You have to check if the stack is empty, right? Because you can't pop an empty stack. Right? There's nothing to return if you do so. So in our case, we're going to throw in a runtime exception to indicate that an error has occurred. So I guess there's actually 5 steps here. Right? And that's bottom. So that's it. You're done your stack implementation as far as implementing the methods in the stack interface. Right? Now, to make this a usable stack class, you probably want to provide other methods. Right? So you probably want to provide a toString method. Right? You might provide an equals. Right? And if you provide equals, you have to provide hash code. Right? So how do you implement toString, for example? Right? Now remember what our implementation looks like. Right? All that we have in our linked stack class is the size, right? The number of elements in the stack, and a reference to the top node. That's it. We don't have all the other nodes. Right? To get to the other nodes, I have to follow the next link in this top element, right, to get to the second one. To get to the third element, I have to follow that node's next link to get to the third. Right? To get the fourth element, I have to follow the third element's next node, and so on and so on and so forth. Right? So it turns out that when you have these linked sequences of some kind, a common operation is that you end up iterating over the sequence. Right? So I need to visit every node in the sequence for some reason. Right? In particular, if you need to get to the bottom node for some reason, the only way to get to the bottom node is to follow the entire sequence of nodes. Right? Or if I need to get to the middle node, I have to follow the first n over 2 links in the sequence to get to the middle node. Right? So reaching an arbitrary element in a linked sequence is big O(n). Right? For toString, right, I need to visit every element in the stack to generate the string representation of each element. Right? And so how do you actually do this? Right? So you write a loop. Well, one solution is to write a loop. Right? Inside the loop, you're going to follow these next links, right, until you get to the bottom node. Right? Now, how do you know you've reached the bottom node? Because the bottom node has a next link that's null. Right? It has no next link. Right? So that's the trick here. Right? You just follow the nodes until you reach a link that's null. So this is the general iteration pattern if you using a while loop. Right? So you can, whenever you need to iterate over a sequence of nodes, you can always just plug this code in. Right? So you start at whatever node you want to start at. Right? Usually in a stack, you start at the top node. Right? If you were implementing a linked list, then you would start at the first node in the list. Right? But you can start somewhere else if you want to, right? If you have reason to. Right? So you so you make a variable n. Right? You point it at the starting node. Right? If n is not null, you can do something with the node. Right? So if n's not null, go ahead and do something with n, right? For toString, we're going to get the string representation of n.elem, right? For something else, you might look at the value of n.elem, right? You might change the value of n.elem or something like that, right? So whatever it is you have to do with n, you do it here, right? And then at the end of the loop, you just advance n one position, right? So to advance n one position, you just write n equals n.next, right? Now, when you reach the end of the loop, right? So when the loop finishes, right, what you have to remember is that n is null, right? So when you reach that line that's commented out, right, whatever you do with n, right, don't try to use a method or access a field of the node, right, because n is null. Doing so will cause a null pointer exception. Right, so that's the general iteration pattern. You can make this a little bit more sophisticated. So for example, sometimes you need sometimes you need access to two nodes while you're iterating, right? So for example, you might need access to the first and second, right? And then in the next iteration, you might need access to the second and third, right? And then the third and the fourth, and so on and so on, right? So if you need to do that, you just make two variables up here, right? One's called m, one's called n, right? You make m point to the node in front of n, so usually it'll be null, right? Then inside the loop, you write m equals n, right? And n equals n.next, right? So now you're advancing two references through the sequence each time, right? If you do that, then down here, m will be equal to the bottom, m will point to the bottom node, right? And if you need three references, for example, you can create a third variable up here, right? So you can move as many references through the sequence as you need, right? And a lot of the more advanced algorithms that you write on these linked structures involves 2 or 3 or sometimes 4 references to nodes as you step through the sequence, right? So for example, you can reverse a stack using 3 node references without having to, and you can do it in a single loop, right? So you can reverse a linked stack or a linked list with by using 3 references, by moving 3 references through the stack or list. Okay, so what is toString? Oh, so this is what iterating looks like, right? So I'm going to start with n pointing at the top node, right? I'm just going to follow, right, when I'm done with the first element, I'm going to follow that next link, right? So that moves me to the next node, right? I'm going to do something with this element, right? And then I'm going to write n equals n.next, right? So n.next is that link there, right? So that'll move me to the bottom node. Right? Do something with the A, right? Follow the link. Now the link is null, so the loop stops, right? So n is null, right? The condition in the loop is while n is not null, so the loop doesn't run, and you're done, right? And n points at null, right? Or n has the value null. So what does toString look like? So I'm going to start with a string builder object, right? So string builder, if you remember, is a mutable version of string. Right, so in other words, it's the class that you should use if you're trying to build a string using a loop, for example. Right, rather than using a plain old string, it's more efficient to use a string builder. So I'm going to start out by setting my string builder object to be the string stack. Right, I'm going to use the general iteration pattern to visit each node of the stack. Right, so I'm going to start n by pointing it at the top node. Right? While n's not null, I'm going to append a new line, and then I'm going to append the string representation of the element in the node. Right? So here you can write n.elem. You can also write n.elem.toString if you want to. Right? But if you just write n.elem, append will automatically call toString. Right? So that puts a new line in, so it goes to the next line, gets the string representation of the element, right? And then we move to the next node. Right? If there's another node, append a new line, right? Append the string representation of the element, go to the next node, right? Until you reach the bottom node, right? When you reach the bottom node, you append a new line, append the element in the bottom node, right? Move n to the next node, now n's null, right? So the loop doesn't run, and now you just return the string representation of the string builder to get the string corresponding to the string representation of the stack. Right, so here we're just using the general iteration pattern. for iterating over a sequence, a linear sequence of nodes. Right? Any questions about that? The only trick here is this n equals n next, right? So once you get your head wrapped around, this is how I move n forward into the sequence, everything else should fall into place. Right? Okay. Notice that our node class, every node has a reference to another node, right? So that means that the node class structure is recursive, right? So each node has a reference to a node, right? That node has a reference to a node, right? And that node has a reference to a node, and so on and so on and so forth, right? Eventually, one of the node's references, next links are null, right? So eventually, you get to a node that has a null reference for its next node, right? But the structure is recursive, right? It's recursively defined. So what that means is, in a linear structure, in a linear linked node structure, you can view any node as being the top node of the stack, of a stack, not this stack, of a stack. Right? So for example, right, in this stack here, right, we know that that node is the top of the stack, right? But if you look at the second node, right, you can say that the second node is the top of a stack of size 2, right? So in other words, the B is the top of a stack consisting of the A then the B, right? And if you look at the A, right, the A is the top node of a stack consisting of just the node A, right? So each node in the stack you can view as being the top of another stack, of a smaller stack, right? Now, when you get that fixed in your head, right, it should become, well, I'm not going to say obvious, but it should become, you should begin to suspect that maybe I can use this fact to write algorithms on these linked structures in a recursive way, right? Because in recursion, every time you make a recursive call, you need to make the recursive call on a problem that has a smaller size, right? If I follow these nodes, right, so if I start at the top node and I go to the second node, right, that's a stack of size 2, which is smaller than the stack of size 3. Right? If I follow this link to the next node, that's a stack of size 1, as opposed to being a stack of size 2. Right? So following these links, you can view as, instead of following links iteratively, you can follow them recursively. Right? So for example, you can write toString in a recursive way. Right? So the way you write toString in a recursive way is you have a public method called toString. Right? It returns a string. It returns the string reference of the stack. Right? We start out in the same way as the iterative version. Right? So I start out with a string builder, right? And the string builder starts out with the string stack. Right? Then I point my node n to the top node of the stack. Right? And now I generate the string representation of the stack whose top node is pointed at by n. And the way I do that is I call a recursive helper method. Right? So I call the method toString Helper. Right? Then this method is private. It's also recursive. Right? It's private because so anybody outside the class can't use this method anyway because they can't see the node class. Right? Remember, our node class is private and nested. Right? So no one has access to the node class. No one outside linked stack has access to the node class. Right? So our method's private. It's going to be recursive as well. So the toString helper returns the string representation of the elements in the stack whose top node is n. Right? So if n is null, right, you have no elements in the stack. Right? So what's the string representation of the empty stack? Well, it's just the empty string. Right? And you're done. Right? Now what happens if n is not null? Right? So if n's not null, then you know that the string representation of the stack is the element sitting in n, right? So it's going to be the element sitting in n plus the string representation of the rest of the stack, right? So that's what the recursive call does, right? So toString helper and next, right, returns the string representation of the stack if you move to the next node of the stack. And so you recursively call the helper method, right? The helper method generates the string representation of the rest of the stack, right? It calls itself, right? Moves to the next node, generates the string representation of the rest of the stack, and so on and so on and so on, until it gets to the end of the stack, right? Where it returns the empty string. Right? And so this the recursive helper method recursively generates the string representation of the elements in the stack. Right? And so you can take the final result and append it to the string builder and then return the string representation of the string builder. Right? And so you can use this pattern here. Right? So using recursion, you can take the general iterative pattern of iterating over elements in the stack, right, and do it recursively instead. Right? Now for these linear linked structures, this is not so useful. Right? Usually it's just easier to write the loop. Right? But if you take CISC124, the data structures course, right, you're going to look at what are called binary trees. Right? So in a binary tree, you've got a node and it points to two different nodes. So in that case, it turns out for many algorithms on binary trees, it's easier to write the recursive version of the algorithm instead of writing the iterative version. All right, so let's look at some more examples of using this node class. Right? So in my experience, especially last term, students have a hard time, many students have a hard time wrapping their heads around the node-based structures or these linked-based structures. So for example, where did Eclipse? There it is. All right. So I've got this class called stacks. Right? I guess it should be called link stacks. So all the this is going to be a utility class, right? So it's a utility class that operates on linked stacks, right? And I want to implement some methods that operate on linked stacks, right? I think I have to make a quick change here to something. Just a second here, link stack. I think I have to make our, yes, I do. Okay. So later on, you're going to, do we do this later on? I think the notebooks does this. So I'm actually going to change the implementation of the node class and make it package private. Right, so in other words, I'm going to remove the access modifier. So when I remove the access modifier from the node class, right, that makes the node class slightly more visible. Right? So in particular, anybody in this any class in this package can now see the node class. Right? And so this is useful when you want to write a utility class that operates on linked stacks. Right? Because now I can access the node class directly, which means I can write methods like toString from the utility class if I wanted to. Right? Because now I can actually access the internal structure of the, I have to do something else. Link stack. I also need access to the top node. So I'm going to make that package private as well. Right? So by increasing the visibility of the fields and the nested classes, and the static nested classes, right, that lets me write methods that operate on the internals of the linked stack directly. Often this is advantageous because otherwise I would have to use just pop and push, which becomes really awkward. Right? Okay, so how do you get the second element from a linked stack? Right? So this looks like an easy problem, and it is, right? But this was asked as an exam question last term. About 80% of the class couldn't answer this last term. Right? But it's actually a really easy question. Right? So how do you get the second element in a linked stack? Well, you know what the top element is, right? The top element's just stored in the top node. Right? So I can always start that way. Right? So node n equals t dot top. Right? Notice I can access the top field because it's package private, and the stacks class is in the same class, same package as the linked stack implementation. Right? So if I just write n.elem, that's the first element. Right? What's the second element? Right? Well, the second element is just n.next. Right? So that's the second node. Right? What's the element in the second node? Well, it's just n.next.elem. Right? And return second. Right? And that's it. So all that question was trying to figure out is, do you understand that these nodes have references to other nodes, right? To the next node in the sequence. right? It was supposed to be an easy question, but like I said, about 80% of the class couldn't answer it. All right, now what else do you have to check in this case, right? Right. If you want the second element from a stack, you have to make sure that there's at least 2 elements in the stack, right? If there aren't, then you can't get the second element, right? So if t.size is less than 2, right, throw some exception. Sure, let's just do a legal argument. Doesn't matter what exception you throw, right? Pick an appropriate one. Right, and that's it. Right? So it's important that when you work with these linked structures that you become comfortable moving from node to node. Right? To move from one node to the next, it's just n.next. Right? Sometimes you have to be careful to make sure that there actually is a next node. Right? But that's easy to check too, right? If n.next is null, then there's no next node. What about equal? So equal, I want to check if 2 stacks are equal, right? But I want to do it from outside the stack, outside the linked stack class, right? So if the linked stack doesn't provide an equals method, then somehow you have to, if you need an equals method, then you need to provide one somewhere else, right? So the way you do it, make a static utility class, put in a static method called equal or equals. I've called it equal. I guess I should call it equals. Right? And this checks if 2 linked stack objects are equal. Right? So you decide when are 2 linked stack classes equal? Right? Well, 2 linked stacks should be equal if they have the same sequence of elements. Right? So the first thing you can check is if their sizes are different, they can't be equal, right? Because they don't have the same sequence of elements then. So that's easy to check, right? So if s.size is not equal to t.size, right, you just return false. Right? Now otherwise, you're going to move from node to node in both stacks. Right? So I need a reference in one stack S, and I need a reference in the second stack T, right? That moves from node to node to node. Right? Each time you move to the next node, you just compare elements in both stacks. Right? So if I reach line 20, right, I know that the sizes of the stacks are the same. Right? So I can just start out. Right? So node, so I'm just going to call this NS, right? And that's going to be the top node of S. Right? And I'm going to call NT the top node of T. Right? And now I'm just going to apply my general iteration pattern. Right? So it starts out as while NS is not null. Right? Now I know that the size of S and T are the same. Right? So if I move NS and NT one step each time, right, then I don't have to worry about checking if NT is also not null. Right? So in other words, I don't have to write if NS is not null and NT is not null. Right? They have the same size. So when I reach the end of NS, when I reach the end of S, I should also reach the last node of T. Right? So I don't have to check both. Right? Checking one's fine here. Right? So if it's not null, I can access the element from NS, and I can access the element from NT. Right? So when I do that, I want to check, are those elements equal? Right? So how do I check if the elements are equal? I just call equals. Right? So if, right, ns.elem dot equals, right, nt.elem. Right? So if they're equal, I can just go to the next node. Right? So ns equals ns.next. Right? nt equals nt.next. Right? Don't forget to move nt as well. Right? If they're not equal, what do you know? The 2 stacks aren't equal, right? So return false. Right? One of the most common errors you see is instead of writing, well, perhaps the nodes get advanced, right? But one of the most common errors you see is that students will write return true here, right? But you can't return true from inside this loop, right? You know that 2 stacks are equal when all of their elements are equal. Right? So what does that mean? You have to loop over all the elements, right? If you exit the loop early, you don't know that the stacks are actually equal, right? So you can't return true from inside this loop, right? You can return false though, right? As soon as you find two elements that are not equal, you know that the stacks aren't equal either. So there you can return false, right? When can you return true? Well, when you've looked at all the elements in the stacks, and you haven't returned false yet. So in other words, I return true once I looked at all the elements in the stack, right? And that's it. So there's an example of iterating over two stacks or over two linked sequences at the same time, right? It's the exact same pattern. You make pointers, or sorry, make references, right, to nodes in both stacks, right? Each time you need to advance one of the nodes, you advance both of the nodes, right? And away you go, right? And that's it. Boop, boop. All right, any questions on these linked structures or implementing a linked stack? Right, so if you can now implement a linked list, right? So a linked list is pretty similar to a linked stack, right? Except when you add elements to a linked list, you add them to the end of the list, right? For a stack, you add them at the front, right? But in a list, you'll add at the end. Let's do one more method. So let's do size. So public static int size of a linked stack T. Whoops, sorry. Okay, so our linked stack class has a field called size, right? It also has a method called size that returns the size of the stack. Right? But in principle, you don't have to keep track of the size of the stack. Right? So in principle, you can always compute the size of the stack if you need it. Right? How do you compute the size of a stack? Well, you just keep a counter. Right? So int n, let's do size equals 0. Right? So all I'm going to do is I'm just going to move from node to node, right, until I reach the end of the stack, or the bottom node of the stack, right, and increase the counter by 1 each time I move to a node. Right? So again, it's just the general iteration pattern, right? So node n equals t dot top, right? While n is not null. Sorry. Right? Just advance n to the next node, right? So n equals n next. Right? When you advance one node, you know that there's at least one. You know that there's one more node in the stack, right? So sz plus plus, and then return sz. And so you can always compute the size of one of these linked structures, right? Instead of storing the size as a field, right? Now, computing the size of one of these linked structures is big O(n), right? Which is why we store a field, which is why we have a field to store the size instead, right? It's much faster to keep track. It's much faster just to return the value of the field than it is to loop over all the nodes in the sequence, right? What's the disadvantage? I have to keep track of the size of the stack. So when I push or pop, I have to change the size, right? If you forget to change the field, you have the wrong size of stack, right? But at least you're not paying a big O(n) price to compute the size of the stack every time you need it, right? But in principle, you don't need to keep track of the size of the stack inside the stack class, right? Inside the linked stack class. All right, any questions about moving from node to node? Right. All right, I'm not seeing anything. I'm going to stop there, I think, today, because the next lecture is something completely different. Well, it's not completely different, but the next lecture is going to introduce some new material. So rather than getting a few minutes into the next lecture and stopping, I'll just start fresh next lecture. All right. Assignment 5 comes out later today. It should come out later today anyway. It's going to be an interface-based assignment.